Hi everyone, happy to meet you again in the air, in the internet. Okay, it is our first day chemistry again. Okay, we are at S1.5 ideal gas. Excellent. It's the end of a section S1. We finished one fifth of the sections of the 6 sections of chemistry. Well done. Okay, so now finish it. Okay. So S1.5 is about ideal gas. Okay, we'll use ideal gas as a tool to find out the amount of gas produced from any reaction. From this information, we can estimate what happened in the reaction and and monitor the reaction rate. It's a very great tool that we really to learn it here. First concept is gas law. Okay, and we have some assumption of ideal gas. Okay, and this assumption come from our daily life experience. We just push the daily life experience observation to the edge, and that is the assumption. First observation, okay, try to move your hand in the air. You feel nothing, right? Nothing blocks you. So you can say that the gas molecule in air is really less dense, right? Sparsely dense populated. You can't feel it. So we said that the gas molecule's volume is negligible compared with the volume of the gas. Okay, this is our observation. You observe it every day when you move around in the air. You feel nothing. Okay? So the assumption ideal gas just push it to the edge. Okay, you said that okay. An ideal gas consists of a moving particle with negligible, really negligible volume, not zero. It's zero, not nearly zero, really negligible volume compared to the volume of the gas. Another observation is that there is no interaction between gas molecule except during collision. In daily life, we know the gas molecule will collide with the wall, right? But not amongst themselves. So the assumption of ideal gas is that the gas molecules are so sparsely populated, so less dense, so they will not collide with each other actually. So ideal gas consists of moving particles with low intermolecular forces. They don't interact with each other. They just collide with the container of the container's wall. First observation, okay, I know the gas molecule will collide with the wall, okay, maybe collide by themselves sometimes, okay, but we never heard the sound, right? It's quiet. And they never lost energy, they don't all fall down after this many collision, low energy loss, okay. And the assumption of the gas is that all the collision are elastic, okay. This term comes from the physics, means that low energy loss is an elastic collision. So the assumption, what is the phi? About the gas molecule, negligible volume, and then a low intermolecular force, and elastic collision, low energy loss. All are the assumptions. Of course, in the daily life, in the real gas, all these assumptions might be possibly correct. Okay, so we need to learn about the real gas. Okay, so the gas molecule has what's problem in the real world. Okay, actually they have a short ring attractive forces. Okay. Silicon has a low kinetic energy. When they move slowly, this attractive force becomes significant. And also the gas molecule has a finite volume, right? Especially when the volume of the gas is small. This finite volume becomes significant. Okay, so actually the gas molecule can move around is a smaller volume. Okay, the effective volume is smaller. So first, the real gas derived from the ideal gas. Okay, particularly and high pressure. So when it is low temperature, low kinetic energy, the short range attractive force becomes significant. High pressure, pressing the gas to a small volume, so the volume of the gas molecule becomes significant. So on the contrary, when we are the ideal gas assumption valid, high temperature and low pressure. Opposite. So in the situation of high pressure or low temperature, the assumption of the gas becomes invalid. Okay, the ideal gas becomes a real gas. Okay, so the law doesn't apply. Okay, the volume of the gas is small in this situation, high pressure and low temperature. So the volume of the gas molecules becomes significant. So the effective space allowed for the gas molecule to move around becomes smaller. Okay. Okay. So some of the space is occupied by other molecules. So the molecule can move through a volume that is smaller than the gas. Okay. Than the volume of the gas. Okay. So and also there might be some cohesive force. Okay. Attractive cohesive forces between the gas molecule. Do you remember the cohesive force? If you learn biology, you learn it, right? Cohesive force is among themselves. Adhesive force is between two different molecules. Okay, so amongst the gas molecules themselves, the force we call it cohesive force. Okay, with the container we call it adhesive force. Okay, so and then the gas molecule might attract each other, so the volume of the gas is smaller actually. So it's a limitation of the ideal gas law. Okay, a real gas does not follow strictly to the ideal gas law. PV equals nRT. Later on we'll discuss this. Okay, from the practical point of view. Okay, but the general trend is still works. Okay, and actually we just talked about this thing, but mathematically we don't have any idea about discussion about the real gas. Even in physics we don't talk about mathematical coverage of real gas. We just bear in mind ideal gas is an assumption. Okay, but we still use the ideal gas law to do all the estimation. Okay? And then graph for the ideal gas. Okay, first of all we need to know we have a 4 variable for gas. So assume we have a balloon of gas. Okay, look at the balloon of gas. How to describe this balloon of gas? Okay, so number of mole of gas molecule inside. Right? You call it N. N is number of mole, and then pressure of the gas inside the balloon, volume of the balloon, and then temperature of the balloon. So we have 4 variables. For the temperature, remember, we always use Kelvin scale. Okay? So Kelvin scale is the degree Celsius temperature plus 273. And then we have this constant molar volume V over N of an ideal gas is a constant at specific temperature and pressure. We call it Avogadro law. We'll discuss it in detail later. It comes from the ideal gas law. Okay? We don't say that V over N is always constant, but it is a constant when temperature and pressure is a constant. Okay, a lot of assumption. In the investigation of an ideal gas, the container is always sealed. We don't want to have a leakage of the gas. Okay, so N is always kept constant. So you look at here, 4 variable. N is always kept constant, always a control variable, such as 3 variables. By the fair test, remember we just change one variable and see the response of the other. Right? So we need to control one more variable in the investigation. For example, for these two graphs, for the first one, we fix the pressure. So low pressure here, pressure is fixed. And then we change the temperature and observe how the volume of the gas change according to the change of the temperature. We find out it is a straight line passing through the origin. Temperature increase, the gas expand, right? By expanding a straight line and also passing through the origin. So we can say they are directly proportional to each other. For the second graph, we fix the volume of the gas. Okay? Increase the temperature to see what happened to the pressure. Same volume, temperature increase, the gas molecule move faster, colliding with the container stronger with higher frequency, so pressure increase. Right? So they are positively correlated, but the experimental result is even stronger. They are directly proportional. Straight line pass through the origin. Of course, why they pass through the origin? Because we choose the origin wisely. We use the Kelvin scale. We use the degree Celsius scale. No, they are not passing through the origin. They are passing through the 273 degrees Celsius place. Okay? Negative. So absolute 0 place. Okay? So it is the reason why we need to use a Kelvin scale. And then next one, we fix the temperature. We observe pressure and volume's relationship. Of course, when volume increase, pressure decrease, right? So they are negative correlated. So obviously they should have a graph convex to the origin. And then we further study, we change the horizontal axis to 1 over V. We find out, wow, excellent. They are straight line pass through the origin again. So pressure and 1 over V is directly proportional to each other. Remember, straight line pass through the origin. Both have to be fulfilled. Just straight line, not enough. Okay. And then we said that, okay, so P and V are inversely proportional to each other. And then in physics, you need to learn the names of these 3 laws. Okay, as a Bowles law, Charles law, and pressure law. But in the chemistry, you don't need. Okay, just learn how to use it. But actually, we just use the combined general gas law. So combine them all together, we have the gas law, or call it a general gas law. PV over T is a constant. When you change from situation 1 to situation 2, compress the balloon, heat the balloon, press the balloon or extend its volume, okay? PVT change, okay? But PV over T does not change, okay? Because it's equals to N now, no matter, so long as no leakage of gas, okay? P over T is a constant. And N is the number of mole of the gas molecule. R is the universal gas content. For every gas, the R are the same. Wow. So we have the concept of partial pressure in previous two curriculum, but not now. And then we have the equation PV equals nRT. By this equation and compare with the equation y equals mx for straight line, and then we lower every relationships, every straight line's gradients meaning. Okay. In IBDP, it's not very stable. Sometimes they call gradient, sometimes they use slope to measure the steepness of a line. So both of them you may encounter. In the curriculum, they always say gradient, but in the past year, sometimes they say slope. Okay. So make sure you know both of them are the same. Okay. In GCE, they use slope too. Okay, and then we have the equation PV over T is NR. Okay, so general gas law. Okay, N is proportional to 1 over T, and proportional to P, and proportional to V. Okay, and that's constant stuff. When we push more gas molecule inside, what will happen? And by all the thing you change the thing, you find out V over N. Molar volume, remember the thing we talked about, equals RT over P. Just depends on T and P. So 1 mole gas volume does not depend on which kind of gas it is. Oxygen, hydrogen, nitrogen in the air, they occupy the same volume, by 1 mole. Oh, it's quite funny, okay? Quite uniform, quite general. But the molar mass is different because M is PS. M depends on which kind of molecule are you talking about. Right? Oxygen gas, nitrogen gas, hydrogen gas, absolutely. They have different M, different density, and both V, so they have different molar mass. So molar volume is a more constant. Molar mass depends on the gas. Okay? And then remember when you do the gas law, because we need this calculation clearly when we do the IA or EE, when you want to use the gas emitted, released by a reaction to do some investigation, bear in mind this calculation, you have to be careful. Okay. For example, the units, okay, we need to use the SI unit Pascal. But in the meter, they always tell you it's the kilopascal, so you to multiply by 1,000 times. Okay. And the atmospheric pressure, we always use it. Sometimes you 101 and sometimes 100. Depends on the situation, accuracy you want. Okay. And the volume of the gas has to be in a meter cube. Sorry. So 1 cm cube is 10 to the power negative 6 meter cube. 1 dm cube is 10 to the power negative 3 meter cube. You need to change it. But when you work out to change the unit, your reward is the end got is correctly the number of mole. Okay. So you also need to add a 273 to the Celsius scale before you plug in the equation. Okay. For example, you have this situation, temperature change from 23, triple, nearly more than triple to 73. Wow, big change, but no. When you add 273 to it, the change is just a little bit. So the volume just change a little bit, not triple. 123 to 144. Also, you need to remember you subtract 273 from the final result to get the daily life Celsius scale temperature of the final result. For example, temperature 43, 45, okay. Degrees Celsius pressure decreases. What will happen to the temperature? Just a little bit decrease, but because you multiply, you add 273. Okay, so the change is great and becomes negative. Actually, become negative 7.6 degrees Celsius. And all this thing will be given in the data booklet. So relax. Okay. And then we have two situations we need to understand: STP and SATP. Okay. One is by the Avogadro law. What is Avogadro law? We learned it already. Molar volume is constant for a particular temperature and pressure. Okay. It is derived from the ideal gas law. Okay. And what is STP? That's a definition, rigorous definition. It's a standard temperature and pressure for comparison. They choose temperature 0 degrees Celsius, the melting point of ice, okay, 275 Kelvin, or 273.15 Kelvin. Sometimes you need to use a 2 decimal place value for calculation accurate. And the pressure they choose at 1.00 times 10 to the power 5 Pascal. Okay. And at STP, okay, ideal gas law is fulfilled. So you calculate all the thing, okay, get the number of mole and then get the mass by multiplying with the molar mass. Okay. And you can have a rough estimation, okay, for ideal gas as STP. Okay. You'll find a molar volume is RT over P. Okay, bring out your calculator, calculate it, and then it's the 22.7 dm cube. You need to remember this one, 22.7 dm cube. Actually, it's given in the data board. Okay, you need to remember. Okay. For the SATP or some, there's another definition for standard ambient temperature and pressure, they choose a higher temperature, 25 degrees Celsius, and a slightly different pressure. But in IB, they choose the same. It's the exact when learning in university. It should be 1.01 times 10 to the power 5 Pascal. But in IB, they both choose at 1.00. Okay, so it's different. I need just 1% difference. Okay, so the molar volume of at SATB is at 24.8 dm cube, not 22.7 because it's a little bit higher temperature, hotter. So volume is bigger. Okay, IBDP requirement, they give you all the data. Just like in IE, you have the data, you internet search for all the things. Okay, you just need to know how to do the calculation, manipulation of the data, interpretation. Okay, more high order thing, not to memorize the thing. So for example, in the chemistry data booklet, okay, 2025, have you downloaded it? Yes, excellent. We might download it and try to print it out and look at it, flip it, okay, every day, because in exam you need to learn how to flip it, okay, in a quickest way, okay. For example, 1, okay, some reference equation, we have the equation PV equals nRT and PV over T equals PV over T in situation 1 and 2. And all the data are here, Avogadro constant 6.02, 10 to the power 23, gas constant 8.31, molar volume 2.27 dm cube per mole. And also these two concepts, but remember, 0.15, sometimes I forget it, sorry, I apologize, okay. Remember 2 digits, 273.15. And then 1 dm cube, 1 cm cube, 1 meter cube, how they convert each other. And STB is 273.15 Kelvin and 100 kBHD. Same. Actually, it should be 108 for this one, but just accept it. Okay. So this is all the thing we need to learn about the gas law. Okay, you will use it 1,000 times later. And later in the even as your research for I and E. Okay, probably you do chemistry. Okay, and then it's a quick tool for us to investigate indirectly what happened in the reaction if they emit gas or they use up the gas. Okay, it's a quick foundation. So we finish S1. S1 has a lot of quick foundation. Right? The gas law, the concept of electron configuration, the mole concept, what's atom, what's nucleus, isotope, and lots of big terms. Okay, and then in S2 and so on, we'll use it, start to use it. Okay. And you will find it out. Maybe you need to go back to S1 to look at the thing again. So thank you for going with me. Okay, it's a quick pleasure to share with you for the chemistry because I love chemistry. I know you love it too. Okay, if you like our video, remember subscribe, like, and then share with your friends. Okay, see you for next video. Bye.